Hello, this is Dean Crumlish. I'm going to show you how to use the analog inputs on a Copley Controls amplifier. One interesting aspect of the plus panel is that we can use the 32-bit floating point filters to filter the analog input before we read it. So I've got the data sheet for the BPL here, ExcelNet panel can open drive. I'm going to look up AN1. So we can see here a general analog input. So the drive has two analog input pins, AN plus and AN minus. Two wires, twisted, shielded, going back to the source of the voltage. So here's an op amp which outputs plus or minus 10 with respect to ground. An op amp always has a ground, and typically it's an analog ground or it finds a path to earth. Either way, that's fine. Sometimes you have a 0 to 10 volt, so you need an offset in the drive. We've got that too, but again, two wires, twisted, shielded. And note, the shield always finds a path to earth. So when you connect it to the frame ground on the Copley, that's connected to earth, so the shield finds a path to earth, so all the electrons coming in go down to earth. The differential instrumentation receiver is an op amp that receives the signal and only looks at the differential, so it has a high common mode rejection ratio. And again, all signals are with respect to ground. And we show the ground connected to earth back at the controller. So, good idea to find a path to earth. So on the signal connector on this drive, we see two analog pins for AN1 plus and AN1 minus. So that's what I'm going to wire my function generator to give us some command signals. It's, again, differential, plus or minus 10 volts. You can exceed that by a little bit. I wouldn't hook up a lot more voltage to the input. Just keep it in the nice range of plus or minus 10. There's a 5K input impedance, and it has 12 bits of A to D resolution. On the plus drives, the A to D converter is external to the DSP, so it has a good effective number of bits, so a good E knob. We'll take a quick peek at the schematic here. Yeah, here's 5.36K across the input, differential input resistance, some high frequency filtration, and the op amp which produces the voltage reference to the A to D converter. So I'm going to show you how I've got things wired up here. I have a function generator, so I can dial in a frequency and an amplitude. That connects to my scope and to the two wires twisted. I don't have the shield wired up, so I violated the shield rule. But it's a good idea to have a shield and a path to earth. Pin 1 is the path to the frame, and the frame is connected to earth. So I've got the ability to adjust the frequency and the amplitude. I can't seem to get much past plus or minus 10, but I can vary it here with the offset. So now we're going to connect CME2 over the serial port, and we're going to run the scope to monitor the analog input. We can also use the control panel to monitor the analog command, so we can see it changing plus or minus 10 volts here. So on the scope, to trace the analog voltage, we go voltage analog command, and trigger type, I did rising edge, channel 1. We can just do 1 volt is good, and then set the trace time to fast, hit record, and there's the same square wave we have on the oscilloscope. I'm going to lock the scale with plus or minus 10, so I can change the frequency, change the amplitude. We can give it a sine wave. So again, this is the analog input, and we can right-click lines, connect dots. You can see the samples. The current loop is sampled at 62.5 microseconds. Actually, it's 4 samples here. So I'm just using the analog input not to drive the current loop, but to either drive the velocity loop or just to read. So the update rate is actually every 250 microseconds for the analog input. That's why we have a little steppish nature there. Of course, besides the frequency of the sampling, 250 microseconds, we have 12-bit A to D resolution on that. So we can continue recording here and get back to the square wave. I did want to show that we do have features to filter the analog input. So this is the value that we're going to read as the analog input. So on the main CME2 screen, we can select the analog on the filter configuration screen, the analog tab, and we can do any filter, low pass, notch, band pass, disable it, Butterworth, Chebyshev, elliptic, single or 2-pole. Well, that is a Butterworth 2-pole, but this is a single pole low pass filter. I'm going to apply it at 200 hertz. So we can see that this, even though we're commanding a square wave, it's getting rounded. So we have a 200 hertz low pass filter applied to the analog command. So in our programs, we can read the analog reference input, and we have to figure out what the parameter is for the analog reference. The analog reference input voltage, also known as the A to D reference input voltage, in units of millivolts, is ASCII parameter 0x1D. There's CAN open equivalence, etc. in RAM only, 16-bit integer. You can see there's analog reference scale factors and offsets. There's used in the current loop, velocity loop, position loop, analog reference, deadband, calibration, that's factory setting, analog input filter coefficients, so this is part of the filter configuration. And some drives even have a second analog reference input, AN2 plus and AN2 minus. That would be like the Zenus XPL. That's pretty rare to see 2 analog inputs on a drive, but it's for the UV analog commutation modes traditionally. So the parameter we want to look for is 0x1D. So I'm connected over the serial port, so I'm going to use Tools, ASCII command line, G for get, R for RAM, 0x1D, and we can see the voltage is plus or minus 9 volts. Okay, so just a quick recap on this. We can use the serial port to get the analog voltage after the filter we want on the plus drives. We can read the analog voltage input over CAN or EtherCAT, depending on which drive you have. Serial multi-drop from node 0 to other drives on a network. So there's just one more thing I'm going to show you we can do. Reading, I'm going to get the analog voltage in an indexer program. So here's an example of a program that can get 0x1D, the analog command input voltage in units of 0.001 volts. I'm storing it to R0. We can do some math, like divide it by 10 and stick it back into the register. And then I could do something with it, like write it down to the peak current limit to limit the current. So in this program, because peak current is measured in millivolts, or tens of millivolts, and voltage is measured in 1 millivolt. 1 millivolt equals 10 milliamps, so that's why I scaled it. And then you can do a conditional jump to sequence 0, and this will loop on the drive. The CVM runs at a 1 to 10 millisecond update range. The standard drive's at 10 milliseconds. The plus drive's more like at 1 millisecond. Okay, thanks for your time.